One more thing I wanted to say about membrane potentials and equilibrium potentials, or show you anyway, is this is a little simulator that kind of lets you play around with different ion concentrations, lets you change the temperature and see what happens to the different values. I'll send you guys this so you can see it for yourself when I can. So this lets you, like I said, play around with the concentrations, and then it shows you what the membrane potential would be. So this graph here is measuring the membrane potential of one of these imaginary cells down here. And what you're seeing, these little balls flying around, are supposed to be the ions moving in and out of the cell. So here we're just looking at potassium. So here it's saying we're able to adjust the inner and outer concentration of potassium, and then the Nernst equation then tells us what the membrane potential should be. So again, if the outer concentration is 10, it's in millimolar, and the inner concentration is 100, then we should see a negative equilibrium potential. And again, because this imaginary cell is only permeable to potassium, then the concentration, the equilibrium potential and the membrane potential should be exactly the same. And so if we adjust either of these numbers, we should get a different value. So if I, let's say, to increase the outer concentration of potassium, so it's a 10 here, if I raise that concentration, let's say, in fact, let's make them equal. Let's say that the concentration of potassium is exactly the same inside and outside. What happens, and what you should expect to happen, is that the equilibrium potential becomes 0. So that means that when the membrane potential is 0, there will be no net movement of potassium. And if I were to flip it and make the outer concentration higher, then the equilibrium potential becomes positive, because now there's so much more potassium outside than inside. But again, that doesn't reflect a typical cell. A typical cell, well, here it lets you have different presets. So the one called generic cell is closer to what we are calling typical. And so again, the outer concentration in this case is 4.5, inner is 120, and so you get a equilibrium potential of minus 87. And again, if this was just the only ion you had access to, or only ion that was permeable, then you would in fact find out that the equilibrium potential and the membrane potential are the same. Then you can switch ions. You can try it for sodium. So here our generic cell has an equilibrium potential for sodium at plus 60 millivolts, and again, that's because the outer concentration of sodium is higher, almost 10 times higher than the inside concentration. For chloride, in our generic cell, it's minus 47, but that's because, again, they've chosen these values as the so-called typical concentrations, or generic concentrations. You can also see the effective temperature if you want to. So again, 37, that's body temperature, but you can see what would happen if, let's say, you had a fever and your temperature is going up. Then you would expect here what would happen is the equilibrium potential for chloride goes down a little bit, and then we'll set it back to 37. For sodium, it raises the equilibrium potential for sodium, and so on. So it does have effect. It's not a big effect for small changes in temperature, but again, that's okay, because hopefully your body temperature isn't fluctuating much more than a few degrees here and there. But then you can even just set it at 37. Then the temperature is sort of locked. But if you want to see what the effect is of multiple ions, you click this tab here for Goldman, and now you're simulating the Goldman equation, which again includes the concentration gradients of all three of these ions, but then it also includes their permeability. So now you see the equilibrium potential for all three ions. This here is equilibrium potential for sodium. Here it is for chloride. Here it is for potassium. Again, we can adjust these. Let's start again at the generic cell values, and we can move them around. But then it calculates for us what the membrane potential would be given the concentrations over here and the permeabilities, which now you can slide around. So here it's saying the relative permeability of potassium is 100. That means it's 100 times greater. Actually, it's 20 times greater than the permeability for sodium, which is here set at 5. So that's how we simulate opening and closing channels. So right now, because again, the sodium or the potassium channels are the ones with the highest permeability, the membrane potential is closest to, or is negative due to that. And then chloride just happens to be in the middle, and so that's why it shows up there. And so we can see what would happen. Okay, let's see if we open some more potassium channels. If we raise the relative permeability, then we should see the equilibrium potential get closer to we should see the membrane potential get closer to the equilibrium potential for potassium. Now, you might ask yourself, what would happen if we just keep cranking up this number? If we just open more and more potassium channels, will the membrane potential just become more and more negative? Would it get to negative infinity? And so let's find out. And what you see is that as you crank this number as high as it'll go, the membrane potential simply becomes equal to the equilibrium potential of potassium. And again, that is the definition of equilibrium potential. It's the what the membrane potential would be if the membrane is only permeable to that ion. Now, of course, it's still permeable to sodium and chloride. That's why it's not exactly the same. So it's negative 87.2 versus negative 87.8. But that's a small difference, and so in this case, these numbers aren't zero, but they're so much smaller than this number that they basically can be treated as zero. So let's reset. Actually, let's reset this back to a generic cell, and you can adjust other things. So you can say, okay, well, what if we open a bunch of sodium channels? Well, then you should expect the membrane potential to become closer to the equilibrium potential of sodium, and in fact, that's what happens. So when we crank that number up. And then you can also show, like we said, that in some cases you can ignore the chloride channel. So let's set these numbers to the values that are kind of in your book. So these are the inner concentration of potassium is 100. For sodium, it's 150 and 15. So we'll set that. For chloride, again, now it's 150 and 13 for what your book calls a typical cell. And then we'll set this number to 40. That's our relative permeability of potassium. We'll set each of these then to 1. And we should see that, yes, the membrane potential becomes equal to minus 65. And that is also happens to be the equilibrium potential for chloride when you have these values. And now you can see that the reason we can take chloride out of the Goldman equation under this very specific circumstance is that no matter how big the permeability of chloride gets, it won't change the membrane potential. So if I crank this number up, you notice the membrane potential does not change. That's because chloride is already at its equilibrium potential. So opening more chloride channels is not going to change the movement of chloride ions. So that's why, again, sometimes we'll see the Goldman equation written without any chloride term. And then if we even if we set it to 0, same thing. So if we close all the chloride channels, has no effect on the permeability or the membrane potential. All right, so again, this is just a little handy simulator. You can play around, adjust different values. We'll come back to it again when we get to action potentials, because we can use this to actually simulate an action potential too. All right, that's all.